to Math 317. This is lecture, I think, 11. And so what I want to do today is I want to talk a little bit about one of my favorite algorithms in all of mathematics, Newton's method, and use this as an opportunity to talk about trying to find the right statistic to look at and to try to figure out what's the right algorithm to look at depending on what you have available. The reason for this is because we are doing the simplex method. And the simplex method is one of the absolute gems of linear programming. When linear programming first came out, it was just of theoretical interest. And if you read the papers, they say, it's wonderful, but you'd have to be able to solve hundreds of equations. And now, of course, you should be laughing at the difficulty of solving, systems of 100 equations. This is no problem. Our smartphones are more powerful than the NASA probes from the 1960s and 70s. The power we have available is absolutely tremendous. So to show that the simplex method runs extremely fast is a little bit beyond the scope of a first course in the subject. It would just take too much time to really delve into that. So rather than going through all the details for the simplex method, what I'm going to do is I'm going to show you how it works. I'm going to motivate that it should work quickly, but we're not going to prove that it actually works quickly. What we'll do instead is we'll analyze some other algorithms and just get a sense of how do you do a complexity analysis. Okay, so there's a little bit more on these slides and I'm going to cover today. If you're interested, if you know a little bit about chaos theory, there's a lot of great articles about how it came to be in studies of the atmosphere. Then there are a lot of wonderful articles about applications in stock market and finance as well. Lots of wonderful places where it arises. All right, so I'm going to skip all this stuff and just go talking a little bit about dimension. So I think this is something we talked about briefly earlier in the semester. I want to really hit home with it now. We have not done these slides yet, correct? Right. So one of the things that's really dangerous is you do math, and then after a while, you ask a fundamental question. You realize you have absolutely no idea what you're doing. You're manipulating symbols. So if I give you the function x squared, what is its derivative? 2x, wonderful. If I give you x to the 3/2, its derivative. 3/2 x to the 1/2. And if I give you x to the root 2, root 2x to the root 2 minus 1. The derivative of x to the r is r x to the r minus 1. Well, how do you prove this? How do you prove what the derivative of x squared is? So the definition of the derivative, so we need to calculate x plus h squared. How would you calculate x plus h squared? Expand it out. We can use Pascal's triangle. We can use the binomial thing. We can expand out x plus h squared. What if I give you x to the 3/2? You would then have to calculate x plus h to the 3/2. There is a trick you can do if you want a little extra credit. Try to figure out how to use the definition of the derivative to calculate the derivative of x to the 3/2. Another way to do this is to say, well, if f of x is x to the 3/2, then f squared is x cubed. The derivative of f squared is 2f prime. The derivative of x cubed is 3x squared. I can now solve for f prime. So we can get rational powers from knowing integer powers. And then the last one is, what does it even mean to take x to the root 2th power? I know what it means to take x squared. That's x times x. X to the 1/2, I'm looking for number y such that y times y equals x. I can understand these things in terms of integer numbers of multiplications. But x to the root 2, you could take maybe a decimal expansion of root 2 and then try to take the limit. It's the limit of x to the 1.4, x to the 1.41, x to the 1.414, and so on and so on and so on, and hope that converges. But the real way we work with this is the exponential function. X to the root 2 is e to the root 2 log x. And now we use the chain rule, and that's how we get the derivative of x to the root 2. And that's how we even interpret what does it mean to raise a number to the root 2th power. And when you look at the Taylor series expansion of e to the x, this makes sense for any real input. You only have things raised to integer powers. So we can make sense of that. And so the reason I'm bringing this up is when you took calculus and you took the derivative of x to the n, did they tell you that the proof only works when n is an integer? Did they talk at all about what happens when you have a rational or a real exponent? Or was this just glossed over? Yeah, usually it's glossed over. And so every now and then it's worth just pausing and thinking about what are the foundations of your subject. So this is a course that is supposed to be a sequel to linear algebra. Can someone define dimension? So what would dimension be? Well, if you can't define it, give me some examples. This set has this as its dimension.
The number of variables that can change within a set.
Okay, so the number of variables that can change within a set. So give me some examples of some sets with their dimension.
Like if you just have a function of x, y, and z, that's a third dimensional function, but and like the set which corresponding to it.
So that's a function of 3 variables, but what's the dimension? So you could say the input space is 3-dimensional. Maybe x, y, and z range in a box, and that box would be 3-dimensional.
The highest power that variables can raise to.
Well, that would be more the degree.
Oh, okay.
So if I give you x squared, x cubed, x to the 4th, it's a quadratic cubic quarter. So the number of elements in the base set. And so what are the possible values for the number of elements in the base set? I'm sorry. So I could have -5 elements in my base set. So let's be very specific. Positive. So you really want to be positive? Yeah, so what about a 0-dimensional set or 0-dimensional space? And so you really want to think, what am I allowing? Yeah, I can see myself allowing something that has 0 dimension. It's just maybe a point. Then I have a line, which is 1 dimension, a square, which is 2 dimensions, and so on. Can you have infinitely many basis elements? Yeah, if you think of Taylor series, your basis is 1x, x squared, and so on. And now you can get into difficulties. Maybe you can have different levels of infinities. If you've done some real analysis, you might have seen that there are different sizes of infinity. And one of my mathematical grandfathers, in fact, was the person who put the final nail in trying to understand some issues about the relative sizes of infinities. What about square root of 2? Could you give me a dimension, a set whose dimension is square root of 2, or do dimensions have to be integers? Can you have root-tooth of a vector? Can you have half of a vector? So when we're using the number of elements in the basis set, it seems clear that it has to be a non-negative integer. But if we expand our definition of what dimension is, we actually can have more possibilities. So just some notation, bold R, blackboard R is the real numbers, R squared is pairs of real numbers, and so on. So dilating a set by R means I take every element in the set and I multiply by R. So if I have a square of radius 5 and I dilate it by 2, I now have a sphere of radius 10. If I have a sphere of radius 5 and I dilate it by 1/5, I now have a sphere of radius 1. So I just multiply every component by that number. And so here is what's going to be called the Hausdorff dimension. So if you have a set S and Rn, if I dilate it by a factor of R, and that gives me C copies of S, then the dimension D satisfies R to the D equals C. So whenever you see anything in math speak like this, you should always think, is there a physical, concrete, simple example which I understand? And let me see if that matches my intuition. So can someone give me an example of a set where we understand its dimension? Simplest set you can think of.
The empty set.
Okay, the empty set. And so I will go back to the book I used my freshman year, which said we will tacitly exclude the empty set whenever it causes trouble. Well, let's see what would happen. If the empty set, we have no elements, right? So if we dilate the set, how many copies of S do we get? We start off with S, and then we dilate it. So how many copies do we get? We still have, I think, the same number of copies, maybe? And you might get d equals 0, so that whatever you dilate it by, r to the 0 equals 1. So I might say that if we have the empty set and we dilate by a factor of r, we still have the empty set. So we have one copy of nothing. We don't have 3 copies of nothing. This is where the language gets a little bit iffy, and you can see why a lot of books say, let's just exclude empty spaces. So what's the next simplest example you can think of?
Set with one element.
Well, that's essentially, you'll still just have one copy. So that will still be 0 dimensional. So if I just have one element, I would just get another one element set. So what's the next simplest dimension you can think of? So these are 0 dimensional sets. So what's an example of a one-dimensional set? A unit line segment. So the easiest example is a unit line segment. I chose to multiply by a factor of 3. And so now we would get a line segment of length 3. So we have 3 copies of our initial set. And so because we want r to the d equals c, r equals 3, c equals 3, so d has to be 1. So at least the notion of Hausdorff dimension reduces to what you would expect for a straight line. What's the next simplest example you can think of? A unit square. So if we take a unit square and we multiply by 3, we dilate by a factor of 3, we now have 9 copies. And so we try to solve, 3 to the d equals 9, so d has to be 2. All right. At this point, it should be clear if I give you a unit box now, it's going to be dimension 3. So this definition at least recaptures our intuition for the standard objects we know and love from the real world. And if you think about it, any object locally is going to look, essentially like a plane. If you really zoom in, if it's, a 2-dimensional surface, it'll look like a box if it's a 3-dimensional surface. So if we just look locally, this is a pretty good definition. So now, how many of you have seen the Cantor set? Okay, this is an absolutely wonderful set. So the way it works is we start off with the unit interval 0, 1, and at every stage, we get to the next stage by throwing away the middle third of every segment that's left. So again, we start off with the initial segment from 0 to 1, we throw away the middle third, and now we're left with 2 segments. The first is from 0 to 1/3, the second is from 2/3 to 1. And I'm just drawing it underneath to show what happens. We now throw away the middle third of each of those, and I'll just draw a bunch of them, just iterating down and down and down. Okay. After a while, it gets very, very hard to start to see the differences as you go further and further down. How many sets do you have at a given level? Initially, we had 1 set, 2 sets, 4 sets. How many will you have? So 1, 2, 4, what's the pattern? 8, and then 16, so it doubles every single time. What about the length of the segments? So initially we have something of length 1, then we have 2 segments and the total length is 2/3. Then we have 4 segments, each of length 1/9, so it's 4/9. For the nth level, what's the total length going to be? What will it be? 2/3 to the n. So the length is going to go to 0. You can show that it actually has uncountably many points. It has infinitely many points. And the reason is we love to write numbers in base 10 or base 2. If you write numbers in base 3, what does it mean to throw away the segment from 1/3 to 2/3? We're throwing away all numbers that have 1 as their first, if you forgive me, decimal digit base 3. It's really their first ternary digit base 3 in their ternary expansion. So if you look at the ternary point, we throw away all the numbers that have a 1. So you're left with numbers that just start off with 0 or 2. Then we throw away everything from 1/9 to 2/9. Again, we're now throwing away everything whose second digit is a 1. And what you're left with is all the numbers whose base 3 expansion never have a 1. So these numbers only have zeros and ones in their base 3 expansion. Well, if you think about it, what does it mean to have only zeros and ones? Well, so I can write it as the sum of, say, an over 3 to the n, where an is either 0 or 2. And then all I need to do is replace the an with an over 2 and replace 3n with 2 to the n. And now I have a number in binary. So you give me a sum an over 3 to the n, I give you a sum of an halves over 2 to the n. And that's now a base 2 expansion. So there's a one-to-one correspondence between the numbers that are left and all the numbers in 0, 1. So this set actually has as many elements as the interval, but it has 0 length. So if you take a class in real analysis, if you take a class in measure theory, you will do a lot more with this. One of the purposes of a 300 level pre-core class is to give you a sense of what will happen if you keep going in math. What will you see? And so here, good shot. And so here we have essentially the same cardinality as the interval, but arranged very differently. And so we can ask, what is its dimension? So we need to think of what's a good number to rescale by, to dilate by. Does anybody have a good thought on what might be a good number to rescale by? 3. And in fact, that's probably why I was doing 3 earlier, to just put 3 in your, just to prime you a little bit. If we rescale by a factor of 3, everything from 0 to 1/3 expands and becomes the whole set. So this part over here will give us 1 full copy. This part from 1/3 to 2/3 expands and is nothing. And then the part from 2/3 to 1 expands and gives us another copy. So we have 2 copies of the set. R equals 3, so we get 3 to the d equals 2, or d is the log of 2 base 3, about 0.63. So we have our first example of a non-integer, in fact, a non-rational dimension. As a nice exercise, one of my students a year or so ago proved that you give me any positive real number and we can find a set with that as its dimension. So the possible outcomes for dimensions is everything. Okay, is this answer reasonable? Whenever you do math, you always want to ask, is the answer reasonable? Well, it's less than 1, good, because we know it lives inside the unit interval, so it's got to be less than 1, and it's greater than 0. I would have been surprised if the dimension was greater than 1. Okay, any questions on the Cantor set? There's other sets you can look at. You can look at Pascal's triangle, and we talked about some of the challenges of computing this. And if we look at putting a dot whenever the component is odd and deleting if it's even, then here's the first iteration, the second, I guess the 4th iteration, and then the 8th iteration. You can begin to see a pattern emerging. And so I've done it sideways. A year or so ago, I actually fixed the video so it goes vertically rather than horizontally. It was just a little bit easier the way Mathematica was to just print it horizontally at first. And I'm just rescaling it so that no matter how many rows I have, I always rescale it so I'm putting it in a fixed size box. And you can see as you take more and more rows that you seem to be getting a fractal structure. And so just doing it so it's vertical, what we're essentially doing is with taking an equilateral triangle, bisecting each side, and then that gives us 4 equilateral triangles, and we throw away the middle. This is a very natural generalization of Cantor. What should I rescale by here? What should I dilate by to find its dimension? So I want to choose something to dilate by so I get a nice integer number of copies of the original set. Any thoughts? For the Cantor set, it was a factor of 3. Yes, 2. So we dilate by 2. This little part over here going from 0 to 1/2 expands and becomes the whole thing. So how many copies will I have if I dilate by 2? I should have 4 copies now. And so r to the d equals c. So since r equals 2 and c equals 3, we get d is the log of 3 base 2, or about 1.58. And what's nice about this is, again, the answer makes sense. It's less than 2. Well, good, this lives inside the plane. It shouldn't be more than 2 dimensions. And it's greater than 1. And we're always going to have the perimeter, so the dimension should be at least 1. Okay, I'm going to skip some of the other stuff on Pascal's triangle, but the whole point of this is that it does reduce this new notion of dimension to something you've seen before, but it now gives us a nice mathematical way of talking about something. And that's one of the great challenges, is to try to come up with what is a good statistic, what is a good concept that we can work with. One of the applications of something like this is trying to figure out the lengths of coastlines of countries. And so imagine you have an incredibly large measuring stick. Initially it's 200 kilometers, then 100 kilometers, then 50 kilometers. The smaller the stick, the more accurately you can measure the coastline, because you can start getting in and out. And what you notice is that as you keep doing this, the approximation for the length of the coastline is changing. It seems to be growing. Does anybody know of any countries that might have a coastline that keeps getting larger and larger and larger with such a measuring? But as your stick gets smaller, it's really going to get large.
Sweden.
Yeah, Sweden. I was about to say, as a hint, Hitchhiker's Guide to the Galaxy and the Mice. Anybody read that? No. So the fjords in the Scandinavian countries, you can start to see that nature of the coastlines much, much better. And so there's a lot of problems you can do. This is called the Koch snowflake. And again, you'll get something where, very similar to the Cantor set, we throw away the middle, but now we put a equilateral triangle where we threw it away. And you can ask, what is the dimension going to be? And it's going to be expanding outward. It's going to be greater. I'm just showing one side of the original triangle. And so you get that, it's greater than 1, less than 2. Why do we care about stuff like this? So much of math is about solving equations. We are going to be working on trying to solve systems of equations with a function that we want to optimize. And so we're going to have lots of different ways of solving these equations. As a theoretical mathematician, you can say, let's just enumerate all the possibilities and go through it. For anybody who has taken a computer science class, you know that this is frequently not even close to doable. We can't just enumerate and go through the space. It would just take too long. We need efficient algorithms to find the solutions. And that's what's so great about the simplex method, is not only will it generate a solution, but it will generate a solution in a reasonable amount of time. After we do the simplex algorithm, we will shift gears and talk about integer valued programming problems. So we've talked about the chessboard problem. We can set this up as an integer programming problem. These are extremely hard to solve. And so we have some methods, and we have ways of trying to get close, but very, very different than the simplex method. And this is the difference between calculus and discrete mathematics. With calculus, when we can vary things continuously, we have great algorithms to find optimals. When we are integer valued and we have to move in discrete time steps, it's much harder to find a path to the best. So if I give you ax plus b equals 0, this should not be hard to solve. If I give you ax squared plus bx plus c equals 0, you should know how to solve this. This is the quadratic formula. You might have seen this by the method of, well, I'll let you answer. What is the method they typically use to prove this? Remember what it's called? Blast from the past. Completing the square. You can also prove that these are the roots by the method of divine inspiration. How many of you have never heard of the method of divine inspiration? Method of divine inspiration is one of the most powerful methods in science. The way it works is you write down the right answer by being divinely inspired and show it works. So I claim that these are the roots. All I have to do is plug in and show that it works. It's a polynomial degree 2. It has 2 roots. What's the problem with the method of divine inspiration? I'm sorry? You need the answer. You need to be divinely inspired. Divine inspiration does not always work. Frequently during examinations, deadlines and whatnot. But for a lot of problems, if you happen to know what the answer is, and you can check, that's valid. So in general, we are not going to be able to find exact solutions to polynomials. So we're going to have to estimate. And so the question is, how can we estimate and how can we do it quickly? One way, of course, is if I want you to calculate the square root of 3, is you can just start writing down numbers and multiplying and seeing, can we do better? As an aside, there is a formula for the solution of the cubic. Here is the general solution, the 3 roots of the cubic, ax cubed plus bx squared plus cx plus d equals 0. There is a reason we don't have you memorize this. Now, you could make it a little bit easier. Without loss of generality, what can you assume about a? 1. I might as well just divide through by a. If a equals 0, then it's not a cubic. Or if you want, you can consider quadratic a degenerate cubic. So let's not go there. We want our cubics to have non-zero leading term. So without loss of generality, you can make a equals 0. You can also adjust so that b, so you can make a equals 1, and then you can translate, you can replace x with x minus r and translate so that b equals 0. So you can clean this up a little bit. It's still painful, but you can clean it up a little bit. Here is just one of the roots to the quartic. And again, for the quartic, you can take a to be 1, and you can adjust so that b equals 0. I think I can zoom in a little bit just so you can get a sense of just how bad this is. Okay. It turns out that there is no explicit closed form solution for polynomials of the degree 5 and higher. So even if you were willing to have a nightmare mess like this, you cannot do that for polynomial of degree 5 or higher. 4 is the highest one where you can write down a solution for a general polynomial of degree d. Okay, so we need a way to approximate solutions. This doesn't mean that if I give you the polynomial of degree 5 that there aren't 5 roots. And it doesn't mean that there's not a formula in terms of the roots. It just means I can't write down a simple formula involving radicals and elementary operations. Once I specify the polynomial, the roots are determined. It's just I can't write down a nice relationship for them. All right. So what I want to do is I want to do the method of divide and conquer. How many of you heard of divide and conquer before? All right, one of our most powerful algorithms. So here's a continuous function, and I'm giving you some information. I'm giving you some information about what's going on near 0. I'm giving you some information what's going on near 1. What can you tell me from this partial plot?
The line crosses the line.
So good. So the function, right? The curve, the plot of y equals f of x has to cross the x-axis, which means it has to have a root. Why is that the case? The intermediate value thing, because we have a continuous function, it attains all the values. Right? Does anybody know why they created transporters in Star Trek? To beam you instantaneously from one place to another. They didn't have money to make a shuttlecraft. The show was just really, really tight on funds. And so they didn't have money to make the set of a shuttle. So like, well, what if we just push this button and then everybody goes from standing in this room and now everyone is down on the planet and now we don't have to make a shuttle. Works for me. Okay, so we'll do some shimmering lights. That's where the transporter came from. If you have a discontinuous function, this is not true. I could have a function that it's negative and it stays negative at maybe negative 0.5 and then jumps up to positive 0.5. But if your function is continuous, it has to cross. Okay. So here's how divide and conquer works. So assume we have a continuous function. For definiteness, let's assume it's negative at a and positive at b, that it must cross somewhere in between. So let's look at the midpoint. Let's look at a plus b over 2. If it's positive there, then there must be a root between a and a plus b over 2. If it's negative, there must be a root between a plus b over 2 and b. And then we do shampoo mathematics, lather, rinse, repeat, just keep doing, keep doing, keep doing. Notice that this is not saying that the only root is between where the sign changes. It's just saying that there must be at least one root. So for example, if I take f of 0 as -1, f of 1 is 3, look at f of 0.5. If f of 0.5 is 2, there's got to be a root between 0 and 1/2. So look at f of 1/4. If f of a quarter is negative, there's going to be a root between f and a quarter and f of a half. So look at f of 3/8. So the algorithm is very easy to implement. Divide and conquer, always look at the midpoint. Is somebody here willing to randomly choose a day of the year? And don't say it out loud. Okay, so I can get to today in 365 questions very easily. Is it January 1st? January 2nd? January 3rd? January 4th? Does everyone believe I will get it? Yes, at some point, yes. Now let's play the game again, but if I'm wrong, you have to say earlier or later. Is it July 1st? So with one question, I've eliminated basically half the year. Well, February is a short month, so I'll go with, is it April 1st? Oh, it really was April 1st? So, got it with just two. But if it wasn't April 1st, I'd pretend it wasn't April 1st. Before. So now I would guess somewhere between January 1st and March 31st. So probably around February 14th.
You're all over it.
We're in phase today. Either that or you know how to kiss ass, one or the other. Oh, well, potentially it could be. But you can see with each guess, and because 2 to the 10th is 1,024, 10 questions is more than enough to guess anybody's birthday. So if you want to try to entertain little kids, I'd guess your birthday in 10 questions or less. Okay, so let's actually apply this. Let's try to find the square root of 3. All right, so my polynomial is x squared minus 3. It has two roots, positive root 3 and negative root 3. And after 10 iterations of divide and conquer, I get that the square root of 3 is somewhere between 1.730469 and 1.732422. And the correct answer is 1.73205. That's not bad. With 10 iterations, I've already got 3 decimal digits. Now, 2 to the 10th is 1,024, which is essentially 1,000. So every 10 iterations essentially buys me another 3 digits. Why? Because every time I iterate, I cut in half the length of my interval where the root has to live. It starts off of length 1, then 1/2, 1/4, 1/8, and so on. So if you want 6 digits accurate, do this 20 times. If you want 9 digits accurate, 30 times. So all you need to do is determine, is the function positive or negative? And that will allow you to figure out, is this my left endpoint or my right endpoint? This is not using that much information about the function. So the intermediate value theorem only uses continuity. What else might you want to use about a function? So what else might you want to use about a function? What else might give you some useful properties? Not just continuous, but so you had to have taken 3 classes in this subject to get to this course. What's the one class that you have 3 of them in your transcript?
Okay.
Calculus. So in addition to continuous, what else might you want to assume about your function? It's differentiable. Is every continuous function differentiable? No. So can somebody give me an example of a continuous function that's not differentiable? You should have a go-to example. Absolute value of x. A more interesting one is x cubed sine of 1 over x. This is differentiable once, but not twice. So just because you're differentiable, or just doesn't mean you're differentiable again, or just because you're continuous doesn't mean you're differentiable. So it is very restrictive to say, I am going to assume my function is differentiable. So the method we create will not be as applicable as divide and conquer. Divide and conquer only assumes the function's continuous. Okay, but if I have more properties of the function, why not take advantage of it? So any baseball fans at all here? So if you know that you're pitching against somebody, if you know that they are a right-hander or a left-hander, the more information you know about them, the more that can affect how you choose to pitch to them. Do you have a lefty or righty pitching against them? If you're playing tennis, if you have some idea, are you serving to somebody who's left-handed or right-handed, that might influence where you serve to. The more information you know, the more you can tailor what you're doing. So it shouldn't be a surprise that the more we know about our function, the better algorithms we have available to understand what's going on. How many of you have taken probability? All right, so I will just focus on you then. So if you've done probability, you know Chebyshev's theorem for bounding the probability that you are at least k times the standard deviation. What's wonderful about Chebyshev is it works as long as you have a finite second moment. But it gives you terrible bounds if you have something that's converging, say, to a Gaussian. And so the central limit theorem often gives you much better bounds, but you need to assume a little bit more in order to use it. What makes Chebyshev so wonderful is it's very general. So let's try to use some results from calculus. I'm going to review some old concepts. So we need equations of lines. We have the point slope form. If I give you a point P and I give you a slope M, then the equation of the line is y minus y naught equals mx minus x naught, right? So it's not too hard. And what this means is if I move x over 1 unit, y goes up m units. Right. So one of the most important ideas in calculus is that locally, every differentiable function looks like a straight line. You can replace your function by the tangent line. And so the new value f of x is approximately f of x naught plus f prime of x naught times x minus x naught. It's approximately where you started, f of x naught, plus your instantaneous speed, f prime of x naught, times the elapsed time, x minus x naught. All right, so we can get the tangent line. And so this is just an example of showing you, for the cubic function, the tangent line seems to be doing a pretty good job over a decently sized region. Proof by example. This is not a valid way to prove things, but just giving you some sense. Here is cosine, and again, the tangent line seems to be doing a decent job approximating it over a good sized interval. So the way Newton's method works is assume f is continuous and differentiable. We generate a sequence of guesses xn as follows. The next guess is equal to take the tangent line with where your point is the previous guess, see where the tangent line hits the x-axis, and that's your new guess. And so when you do the algebra, you get your new guess xn plus 1 is the old guess xn minus f of xn over f prime of xn. So let me just show what's going on. So here's my initial guess x naught. I draw the tangent line at x naught, and so it hits the curve at the point x naught f of x naught. The slope is f prime of x naught, and I draw the tangent line and it hits the x-axis at some point which I'll call x1. If my function was exactly a straight line, then this would be the 0. But it's not, so this is probably not the root. So now what I do is I do a new tangent line at x1. And so I have the point x1 f of x1 with slope f prime of x1, and I see where that hits. And I call that x2. And I keep going and going and going, and the hope is that this will converge to A. So Newton's method does not always converge, and so there's a lot of great questions you can ask about, will it converge, and if so, how quickly? All right, so if you do some algebra, if you want to find square roots, if I give you, for instance, f of x is x squared minus 3, after you do some algebra, you get your next guess is 1/2 previous guess plus 3 over previous guess. If instead of trying to find the square root of 3, if I wanted the square root of 5, how do you think this formula would change? So if I wanted the square root of 5, what would you guess the formula? What would the change be? Yeah, 5. And so let's see how good of a job this does. There's a very natural choice of xn to make. What would be a really natural choice to plug in if we're trying to get to the square root of 3? So what would be a good choice of xn? We can't do it, but what if we were lucky? What would be a really good lucky value of xn to take? So we're trying to get to the square root of 3. And what this tells us is, if we start off with the square root of 3 equals, 100, this would then tell us the next guess is 1/2 100 plus 3 over 100. That's approximately 50. What would be a really interesting initial guess for the square root of 3? Nope.
2.
Nope. Square root of 3. Right, what if we happen to guess the square root of 3? Then we would get root 3 plus 3 over root 3. That's 2 root 3 divided by 2 is root 3. So it's stable. If you happen to hit the square root of 3, you stay at the square root of 3. And so, if you go through, I'm not going to go through and do the algebra. It's all on the slides. But when you do the algebra, it comes out very nicely. You get this beautiful formula. If you want to do cube roots, fourth roots, gives you a beautiful formula as well. So these are the slides that converted me to being, I want to do math through my life and not physics. So let's try to calculate the square root of 3. Does everybody agree that 2 is not a phenomenal initial guess? I'm not stacking the deck. So if I start off with 2, my next guess is 7/4, which is 1.75. Not bad. The answer is 1.732. My next guess is 97.56. You'll always get a rational number. 1.73214 versus 1.73205. All right. My third guess, 1.7320508. The correct answer is 1.7320508. Oh, I can't actually tell the difference anymore. I need to go even further than that. Every time you do another iteration of Newton's method, you double the number of decimal digits. You want to talk about fast convergence. Divide and conquer. We're chugging around. Every 10 iterations gives you 3 more digits. Here, we double the number of digits of accuracy. So I did the 5th one, and you have to go so incredibly far before we have a 669, 678, before you finally find a difference between the two. It is absolutely amazing how quickly Newton's method works. This is the ideal algorithm we're trying to find in life. Something that's easy to implement, just nice, simple rationals to manipulate, and converging incredibly fast. Now, of course, you have to develop the theory to prove that it converges. And if people are interested, I will post in the slides some questions you can do, which will lead to how you actually show that this converges quickly. But let's end with a little bit of a game. So let's take the polynomial x squared minus 1, which has 2 roots at -1 and 1, and we will color every point on the real line red if it converges to the red root, and blue if it converges to the blue root, and purple if it converges to neither. Can anybody give me any suggestions of what should be colored red, what should be colored blue? What do you guess would be colored red? What do you guess would be colored blue? Good. Everything to the left of 0 is red. Everything to the right of 0 is blue. And then 0 would be, neither. And in fact, if you looked at the algorithm, we can't divide by 0. So Newton's method does not want to be run at 0. And it is exactly what you would expect. All right, so let's see how your intuition works in higher dimensions. So we can look at x cubed minus 1. So this has 3 complex roots. Now, what's nice is you can actually factor this. It's a difference of 2 cubes. We know when x equals 1, it's a root. So it's x minus 1 times x squared plus x plus 1. So you can factor that, use the quadratic formula, and we get our 3 roots. 1, -1/2, plus or minus I root 3 over 2. So I have 3 points in the complex plane. I will color them red, blue, and green. Before, you said anything that was negative went to the red, anything that was positive goes to the blue. What would you guess goes on here? What do you think converges to red? Give me a nice phrasing in English. You converge to the red root if you are closest to the red. So how would you determine which point is closest? What does this divide the complex plane into? It's symmetric up the wazoo. So how can you tell which points are closer to red versus green? So along the x-axis, they're equally distant between red and green. So how do I tell if you're closer to red than green? If your y-coordinate is positive. So in fact, it splits the plane into 3 regions, 120-degree angles. And I would guess that everything in the far right would go to blue, everything in the upper left would go to red, and then like the bottom left would go to green. when you actually do it, you get an incredibly strange fractal shape. And so the start of today's lecture was on dimensions. And one way to look at a lot of the fractals that arise is extreme sensitivity to initial conditions. This is a point I really want to make in this class. When you're trying to solve problems, you need to know how sensitive is your solution to the values you start with. So one of my former students now does climate models. And I'm not going to get into whether or not global warming is happening or global warming is not happening. What I will say is he has noticed that in a lot of the models, if you change certain key parameters by extremely small amounts, you get very different predictions as to what's going to happen. And what this means is you have to be very careful about dealing with consequences of models if you are not sure about the values of some of these parameters. And how accurately can we measure these in the real world? If you look at some of the papers that were used to justify the COVID lockdowns, you have a lot of mathematical models. Can you trust all of their predictions as to what would happen? So I really want you to be aware that there are many situations where we have what's called extreme sensitivity to initial conditions. This is one of the first places where KS was found. All right, so let me see if I can quickly get this to work. I'm trying to expand this. Newton's fractal. All right, I'll just do this one. What I normally do is just not loading on my computer right now. So this is zooming in, getting closer and closer and closer. And you're seeing this incredible sensitivity to initial conditions. And all these, of course, you have to have some kind of music playing in the background. All right. Okay, so the whole point of this is that when you have extreme sensitivity to initial conditions, if you move over ever so slightly, it's not letting me take over again. So when you have extreme sensitivity to initial conditions, if you change things by ever so small amount, you can have wildly different behavior. And so when you look at the boundary, okay, so yeah, so last thing I just want to, when you look at the boundary over here, there's not that much difference between this point and this point, and yet we change completely which route we go to. So, again, this is a first course in this subject. We're not going to get into everything, but there's extreme sensitivity to initial conditions. When you have these algorithms, you always want to know what is the danger. Could you get caught in a local versus a global? Could you go to the wrong point? All right, so this is a good place to stop for today. We will then continue with phase 1 and phase 2 on Wednesday and just talk about how that's done. And right now, if I had to guess, I would say good chance Friday will be Mountain Day.